Welcome to the Bodhi Academy. My name is Amsha Classo, and in today's video we will continue with the last part of the chapter Equilibrium, Class 11, Chapter 6. Now, here we will talk majorly about the factors that affect the acidic strength, then some of the common ion effect in the ionization of acids and bases, then we will move to the buffer solution, then its types, then we will know something about the Henderson-Hasselbalch equation, the buffer capacity, solubility, equilibrium of sparsely soluble salts and solubility product constants, and the common ion effect on solubility of ionic salts. So these are the last topics that we are going to cover in this chapter. Now starting with the factors affecting the acid strength, having discussed quantitatively the strengths of acids and bases, we come to a stage where we can calculate the pH of a given acid of the solution. So now, knowing all of the strengths of acids and bases, now we are at a point where we can actually calculate the pH of any given solution. But the curiosity rises about why should some acids be stronger than the others. So now the question that rises is, even in the acids, what we were doing, we were differentiating them into acids and bases. Then we said that amongst acids also, some acids are going to be strong acids and some are going to be weak acids. So why is this need required so as to differentiate that why some are strong and why are weak? Now, what are the factors that are actually responsible for making them strong? So, as to why some of the acids are strong, what factors are involved in this? The answer lies in its being a complex phenomena, but broadly speaking, we can say that the extent of dissociation of an acid depends majorly on two things: the acid, the strength of the acid, and the polarity of the HA bond. So, majorly it depends on two things. One is the strength and second is the polarity of the HA bond. Now in general, when the strength of HA bond decreases, that is the energy that is required to break a bond is less, the HA becomes a stronger acid. So whenever you have a bond between H and A, say here the energy that is required to break this bond is less, then we can say that HA becomes a stronger acid. Also, when HA bond becomes more polar, that is the electronegativity difference between the atoms of H and A increases and there is a marked chain separation, cleavage of the bond becomes easier, thereby increasing the acidity. Now, with reference to the polarity, what we are saying is that if the electronegativity difference which is there between both HA and A, if it goes on increasing, then the charge separation will be quite larger, and in that case the cleavage of the bond becomes much easier by increasing the acidity. Okay, now but it should be noted that while comparing elements in the same group of the periodic table, HA bond strength is a more important factor in determining acidity than its polar nature. So now when we are looking in the same group, okay, in the same group where most of its properties are going to be very like they won't have a huge difference, we can say. In that case, we majorly look at the HA bond strength more over the polarity of that polarity of the compound that is present. Now, as the size of A increases down the group, HA bond strength decreases and so the acidic strength increases. For example, now what we are saying is that A which is there, okay, that we can consider say are halogens, okay. Then what we are saying, as we go down the group, the size increases, okay. HA bond strength that is there, that will decrease. If size increases, the bond strength will decrease and so the acidic strength will increase. What is going to happen as we move down, say, okay, as we move down, size will increase, correct? So say we have fluorine, okay, say we have fluorine we have, so its size is say this, then we have say chlorine, its size is going to be this, then Br size will be this, and say last we have iodine, size is this. Now what will happen here, that what we are saying is that the HA bond strength will decrease, okay. So in this case, if we see, the electrons are going to be very tightly packed, okay, and therefore the nucleus is going to act on all of these electrons which are present. But if you look at iodine over here, the nucleus won't be reaching so much as to at the last. So what will happen? The bond strength won't be as strong as in the first case. So therefore we say that when we go down the group, the size increases, but the bond strength will decrease, and therefore in 10 it will increase the acidity. But when we discuss elements in the same row of the periodic table, HA bond polarity comes into picture. That becomes the deciding factor for determining the acid strength. Now this was about the same group. Now when we are talking in terms of row, then what we are going to look at more specifically, we will look at the polarity. So as the electronegativity of A increases, the strength of the acid will also increase. So example is say CH4 we have NH3, H2O and HF. So HF will have the highest acidic strength and its electronegativity also will be the highest. Now common ion effect in the ionization of acids and bases. Let's consider an example of acetic acid dissociation equilibrium represented as. So acetic acid, it is dissociating into H plus, its proton, and CH3OO minus. So here what we can say, we write the product upon the reactant. So addition of acetate ions to an acidic solution results in decreasing the concentration of hydrogen ions. Also, if hydrogen ions are added from an external source, then the equilibrium which is there, it tends to move towards the undissociated acetic acid, that is in the direction of reducing the concentration of hydrogen ions. So now what they are saying, when we add acetate ions, okay, to an acetic acid solution, resulting what will happen, that there will be a decrease in the concentration of the hydrogen ions that are present. Also the hydrogen ions which are added through the external source, okay, through some other salt which is being added, in that case also the equilibrium which is there, it moves towards the undissociated side, wherein the CH3COOH is not dissociated, it moves in that direction, and in 10 it reduces the concentration of hydrogen ion. Now this phenomena, it is an example of common ion effect, because here see, we are already having acetic acid which has acetate ions, and in 10 also we are adding more of it. So the common ions are being cancelled out. It can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium. So now already we have the acetate ions. To that already in the acetic acid we have the acetate ions. Externally we are also providing more of it. So we are already, what we are doing, we are dissociating the equilibrium. Thus we can say that the common ion effect is a phenomena that is based on the Le-Chatelier's principle. Now in order to evaluate the pH of the solution resulting on addition of 0.05 molar acetate ion to 0.05 molar acetic acid solution, we shall consider a simple dissociation of acetic acid. So here it is getting dissociated H plus and acetate ions. So its initial concentration 0.05, here 0.05 molar. Now let X, what we are considering, the change in extent of ionization of acid that is happening. So minus X plus X and plus X. Why? Because this is acetic acid that is getting reduced, so negative sign, and this is more and more is being formed, so positive sign. So equilibrium concentration will be 0.05 minus X and 0.05 plus X. Therefore, if we have to write equilibrium constant over here, we will write it as H plus. So substituting those value, Sk is very small for a weak acid, that it is going to be the K value is going to be less than 0.05. Thus we can say that 0.05 plus X, approximately it is equal to 0.05. Thus when we put it in terms of the pH formula, we get pH equals to minus log of 1.8 into 10 raised to minus 5, which is around 4.74, which tells us that it is a weak acid, because we are moving more towards the basic side. So if it was around 1 and all, then we could say it is a strong acid, but it is around 5, so it is a weak acid. Now next, let's go to this final topic, that is the buffer solutions. Now a buffer solution is a solution that resists change in its pH upon addition of small amount of an acid or base. So what we are saying is that a solution, okay, which can resist a change in pH, as in when say you are externally adding acid or base, that change which is happening due to addition of new substance, that change is resisted by the solution. It will not show up onto the pH scale. Such solutions are called as this buffer solutions. Buffer solutions are important in maintaining a stable pH in many biological and chemical systems. Now many solutions are mainly of two types. One is the acidic buffer and one is the basic buffer. So acidic buffer, they are formed by mixing a weak acid with its salt, okay, conjugate salt as in its conjugate base. Example, say we have acetic acid, to that it will be formed by adding sodium acetate, that is its conjugate base we can say, or its salt. pH of acidic buffer is going to always be less than 7. Basic buffers, they are formed by mixing a weak base and its salt, that will be its conjugate acid. Example, ammonium and ammonium chloride. Its basic pH will be greater than 7. Now to calculate this pH, okay, pH of buffer solutions, we use a special equation that is known as the Henderson-Hasselbalch equation. Now this equation is given by pH equals to pKa plus log of A minus upon HA. Okay, whatever acid is whatever weak base or acid we have along with its conjugate base, it is the log of that solution, as in we have to consider the concentrations. So here see, we have pKa is the negative algorithm of the acid dissociation constant, this we already know. A is the concentration of the conjugate base, okay, in the numerator that we have, that is the concentration of the conjugate base or the salt that we have taken. HA is the concentration of the weak acid, that is in the denominator we have the concentration of the weak acid. Now let's look at this buffer capacity. Buffer capacity is the amount of an acid or a base that can be added to a buffer solution before a significant change in pH occurs. So when we say saturation, okay, what do we consider in that terms? When we go on adding and it is that point beyond which the solution can no longer dissolve anything, okay, it starts to precipitate out. Same way in buffer capacity. So buffer capacity, what we are talking about, it is the amount that we add which does not usually bring about a change. So like that we can add a certain amount of it, okay, until and unless we start to see a change. So that amount right before we start seeing a change, that is known as the buffer capacity. So as to that much amount it can take and it will not show any pH change that occurs. So the buffer capacity is higher when the concentration of acid and its conjugate bases are higher or nearly equal. So buffer capacity, what they are saying, it is going to be highest or it will be higher when concentration of the acids and the conjugate base are also high or when they are nearly equal. Next, let's talk about the solubility equilibria of sparingly soluble salts, which are partially dissolving salts, okay, not which completely dissolve. So in this case, a salt that dissolves to a very small extent in water to give a saturated solution, okay, a salt which barely dissolves, okay, but yet even if you add little, then it will dissolve very less from that little also and rest will remain, so that automatically becomes a saturated solution. So those types of salts we are talking here. So the dissolution of a sparingly soluble salt in an equilibrium process. So for example, let's consider the dissociation of silver chloride. So that is AgCl. It will dissociate into Ag plus and Cl minus. At equilibrium, the concentration of ions in the solution remain constant. The solubility of such salt is represented by the solubility product constant. Now for such solutions where the solubility or the saturation is occurred so quickly, here the solubility for such salts we determine it by using something known as the solubility product constant, that is given by Ksp. Now the solubility product constant in an equilibrium constant for the dissociation of sparingly soluble salt in water is given as, say we have AB twice, okay, so which dissociates as AB, which will go as A plus, and 2B minus, 2 molecules of B are there. So in that case, this solubility product constant can be written as the concentration of A plus the concentration of B raised to the stoichiometry value that is given. So A and B are going to be the molar concentrations of ions at equilibrium. Say for salt AgCl, we could express it directly because this is 1:1 ratio. We will directly take the concentration of Ag plus ions and Cl minus ions. One thing to remember is that when the value of Ksp is large, okay, the salts are going to be more soluble. For sparingly soluble salts, Ksp is usually very small, okay. Last topic is common ion effect on solubility of ionic salts. So the common ion effect refers to the decrease in solubility of sparingly soluble salts when a solution already contains one of the ions involved in the dissociation of the salt. So now this concept comes majorly into picture when, say, I have one simple example. If I have to take same example, we will talk with reference to acetic acid. In that, I already had acetic acid in which acetate ions were present, correct. I was externally also adding acetate ion. So what was happening? One ion was common, correct. So in that case also there is some difference that occurs into the solubility. So that is what when we refer to when we talk about common ion effect of on solubility of ionic salt. For example, say we have calcium sulfate CaSO4 which is dissociating into Ca2 plus and SO4 2 minus. Now if a solution of calcium sulfate is already prepared with Ca2 plus ions, okay, so say there is already presence of calcium 2 plus ions, the solubility of CaSO4 will decrease because the system will shift to the left due to increased concentration of common Ca2 plus ions. So say we have CaSO4 solution, okay, that is already going to dissociate into Ca2 plus and SO4 2 minus. In that, say through external source I am adding calcium ion. So what will happen, they are saying, is that the system or the equilibrium will shift towards the left, which is due to left as in it will shift towards more towards the reactant side. Why? Because there the concentration of Ca2 plus is even more, okay. This happens according to Le-Chatelier's principle, which states that if a system at equilibrium is distributed by changing the concentration of one of the compounds, the system will adjust to counteract the change. In this case, the increased concentration of Ca2 plus will shift the equilibrium towards the solid salt, thus decreasing the solubility. So we know Le-Chatelier's principle. What does it says? If any change is occurring, okay, the overall solution will try to adapt to that change that is happening, and equilibrium will also change in such a way to counteract the change that is occurring. Same thing is happening when we take this Ca2 plus ions. It will shift towards the calcium sulfate that is present. Why? Because there more and more Ca2 plus ions are being generated, and that will in turn decrease the solubility. Another example would be, say, adding Na2SO4 which also has sulfate ions to a solution of calcium sulfate. This will decrease the solubility of calcium sulfate because the common sulfate ions that are present, that is SO4 2 minus. Okay, so that was it for this whole chapter of equilibrium. Please don't forget to like, share and subscribe to the Bodhi Academy.